And represent.
Alright, good afternoon everyone. Thanks for coming out to our senior design presentation. Our project was named Make It Rain, and for our senior design we decided to make a solar powered drip irrigation system. Again, my name is Dean Hall.
I'm Kenneth Maranza.
I'm Jeff Zed.
And our advisor is Professor Shobak Kirshvan, and we're all from the Department of Mechanical Engineering. And the overview of what we'll cover today in our presentation is we'll start with our customer need, then our solution that we came up with to meet that need, and then we'll end with our evaluation of whether or not our solution met their requirements. So starting out, our community partner was Walden West, which is an outdoor science camp for 5th and 6th grade students that's located in Saratoga, California. And they have an emphasis on hands-on learning, as well as hands-on learning with an emphasis in sustainability in the environment. It is located outdoors. And there's approximately 12,000 students that visit the site per year, and approximately 200 students that visit per week during the school year. And the requirements were that there is domestic water currently at the camp, but since it's in the hills, it's quite costly to use this water, and due to the high volume of students that go in and out of there, there's not much water, or there still is water to irrigate the garden, but they prefer a method by using rainwater instead. And our project was going to be a second phase to a project done 2 years ago named Sunflower, which collected excess rainwater at the bottom of the hill and pumped it to the top of the hill where their garden currently sits. And our contact at the camp wanted 300 gallons of water on demand to be able to irrigate their garden, as well as they're required to, he asked us to use alternative storage to be able to store this water because it could be used as a component of education for the students that visit the camp. And as displayed on the screen here, our project's goal was to be the second half of this project as mentioned earlier, and to allow sustainable energy storage to be used to pump water or to drip irrigate their garden successfully with the 300 gallons. And here's our initial system diagram. So it's going to go. So it would go from the 1,100 gallon water tank, which would be pumped using the power from solar panels, and it would pump into the pressure tanks here, and then it would get connected to their current existing drip irrigation, which is already there. And based on our research we found done by the University of California at Riverside, the optimal flow rate for drip irrigation in a garden with a 3/4 inch PVC pipe is around 2 to 4 gallons per minute. So that's the range that we would set our target for the pressure tank to release. And now I'll pass it to Ken to cover our pressure tank, or our pump and pressure tanks.
Okay, as you said, the first part I'll be talking about is the pump. And when selecting our pump, we wanted to note the losses that we would have to overcome in our system. So that's what this calculation is here, the total dynamic head, which is basically the difference between the suction head or the discharge head and the suction head. As you can see, both parts of this calculation have three similar components, which is the head loss, which is from the height differential, the head loss from pressure, but in this case it's only at the discharge end due to the pressure tanks on the discharge side, and the head loss due to friction in the pipes. And through our calculations, we found that we had a total dynamic head of about 16 meters. And from that number, as seen here, we calculated our hydraulic pumping power, which is the power output of our pump that our pump is providing, and shown are some constants that we used, such as the flow rate of 4 GPM, which is the pump spec, and density of water and gravity as well. Through our pump selection stage, we narrowed it down to a diaphragm pump and a centrifugal pump. Mostly due to cost, we wanted to keep our costs down, so that's why these two pumps were selected. And typically, centrifugal pumps discharge vertically and require more power to overcome gravity. And our system was a fairly linear system our piping was very linear, and we didn't have to go up and down. So we figured that the diaphragm pump was more suitable and met the requirements that we needed for this system. This is the pump that we selected, is the Aquatech 12-volt DC pump. The reason for choosing a DC pump was, as Dean said earlier, we're using solar panels, and as we know, the sun's energy is not, or sunlight is not consistent. So this pump would be able to run no matter what the sunlight was, whether it was peak or not peak. The pump would just run proportionally to whatever the sunlight was available. And through the 12 volts and the 11 amp draw that you see up there in the spec. That's how we calculated the power required by our pump to see what our efficiency was of this pump in our system, which is about 30%. And as Guy mentioned earlier as well, this is the main component of our project. This is our energy storage component. It was used also as an alternative means of storage to show the students at this camp that there are other means of storing energy besides batteries. And this is where the water is moved to from the pump. So the way these pressure tanks work is there are two compartments. It's airtight, so there's an upper compartment, which is where the air is. It comes at a pre-charge of about 30 psi. And the lower compartment, which is a rubber bladder, which is where the water will be held. As the pump moves water into the lower bladder, the volume increases in the bladder, and it compresses the air in the upper chamber, thus increasing the pressure on the water. And then this water will be held in the tanks until they will be released into the drip irrigation system. And so for our pressure tanks, we wanted to see what the minimum required pressure, initial storage pressure is for effective drip irrigation. As Dean said earlier, we would like 2 to 4 GPMs, and we needed this friction factor to calculate our initial storage pressure for these pressure tanks. As you can see, we started with Bernoulli's, which would represent the ideal case of if there were no friction losses throughout our system, to be about 16 psi. But knowing that there would be losses throughout the system, we calculated the pressure drop to be about 11 psi throughout the system due to friction losses. So this resulted in us needing a minimum required storage pressure of 27 psi in our pressure tanks. And this is the model of pressure tanks that we decided to go with. It's the Amtrol ST210B. As you can see there, it they hold 86 gallons, and we decided to go with 4 of these tanks to meet the customer need of 300 stored gallons. And we also decided to go with 4 smaller tanks instead of 1 large tank for ease of installation as well as shipping, and for redundancy. In the case of if 1 tank should fail or up to 3 tanks should fail, this system will still be able to run just with less stored water. And these are 2 controls, the controls we're using for the system. As I said earlier, there's a minimum pressure storage that we need in order for effective drip irrigation. So we have a pressure regulator to slow down the flow rate of our water from the pressure tanks to the system, because with higher pressure comes a higher flow rate out of these pressure tanks. So this pressure regulator will make sure that the water going through the drip irrigation system isn't too fast for effective drip irrigation. And this timer circuit is in place just to automate the times of the day when Walden wants to to irrigate their garden, so that they don't have to manually go out there and turn on the system and shut it off. And now I'll pass on to Jeff for the electrical components and power storage.
Obviously, we would need something to power the pump, which will move the water through the pressure tanks, like Ken said. So our first decision for solar panels was to figure out which type of solar panels we would need. We first narrowed it down to the photovoltaic and the thin film modules because they're on the cheaper end. At first, we were thinking of going with the thin film modules because they're the cheapest, and as also the previous project, Sunflower, had used them as well. However, our contact at Walden West specifically asked that our PV modules, or our solar panels, be able to be pole mounted onto a pole. And because that photovoltaic modules already have racks which can be easily set up on a pole, it was able to split time and money by getting the photovoltaic modules over the thin film. First, and then after that, we need to find out what type of solar panels that we would need. From this, we found out the power that the pump required, and we divided that by the derating factor. The derating factor is a factor which is taken into consideration, which takes into consideration deficiencies in the solar panels, such as if the panels are dirty, if they're shading the temperature outside, and so on. So the power the pump required was 132 watts, and we divided that by 0.77 to get 171 watts. Because of this, this is the minimum amount of power that our solar panels would need to supply. And from that, we found that 130 watts was available, so we decided to get 2 panels at 130 watts. So we selected the Sharp brand photovoltaics. The notable things to know about this is that the max power is 130 watts. The voltage we will get is max is at 17.4, but we'll usually get around 12. And the max current for each panel is 7.5 amps. And then now I'll pass it to Dean to talk about some changes that we had in our system.
So I'll walk you through our design process from our initial design to our redesign. Now our initial design, as we just talked about, was a standalone system. The panels would just be connected directly to the pump, and it would just water when it needed to during the day. However, we found out that we'd have excess sunlight, so we needed to be able to store this extra energy somehow. And at the same time, there's also another senior design group called Blades of Power, which is installing windmills at Golden West, and the power that they're generating is not currently being used for anything. So we decided to kill 2 birds with 1 stone essentially, and install a battery bank prior to our pump so that it can get consistent power, and we can store the excess power from our solar panels as well as the power that they generate to be able to run our pump and operate our system. And I'll pass it back to Geoff to talk about our electrical system.
So as you can see, this is the updated system diagram. The only difference from the system diagram we had before is that red box there. And what we're implementing in that red box is the solar panels will go through a combiner box, which will then go to a fuse box, which will then go to a charge controller, which will then go through a battery, which will power a pump. I'll go over each part in the next slides. So the first one is the combiner box, and what this does, it takes in 4 wires, the positive and negative of the 2 panels, and out will come the one positive and the 1 negative. And inside the box, we will be placing the panels in parallel, so so our panels will be around 12 volts at 15 amps, which our pump requires. Also, what this is for is so there's a fuse breakers in the box. So if we need to turn one or the other or both panels off, in case of an emergency, we can simply turn off the switch, or if it has too much power, it'll break and shut off our system by itself. The second box is the fuse box, which does the same thing as the combiner box. It's pretty much a safety switch for our solar panels, our batteries, and our pumps. So say if our battery is going to be dangerous to the kids or a shed, it'll just shut it off and no damage will be done. Our next component was our charge controller. We decided to go with the Morningstar TriStar charge controller MPPT TS60. The main reason why we got this charge controller was because, the use for charge controllers, so the solar panels can communicate with the battery and make sure that the battery is not receiving too much voltage or amps from the solar panels. The main reason why we selected this charge controller was because of the MPPT, which stands for Maximum Power Point Tracking. And what this does is it pretty much makes the most efficient use of the power that our solar panels are generating to our battery. So what this will do will send the best amount of current and voltage to the battery. Another reason why we got this charge controller was because of the data logging feature. And what this does is it allows remote access to our solar panels, and we can see from here or home or wherever what our solar panels are receiving, instead of actually going up to Saratoga and viewing what the solar panels are receiving. As of right now, we do not have Wi-Fi at that location, so we will need to do that in order for remote access, but we'll have that in the near future, so remote access will be available. And then lastly, we have the battery. We decided to go with a 100 amp hour Deca gel battery. The reason why we picked this is because our pump requires 15 amps, and we would be charging it for 1 hour twice a day. So pretty much we would need 30 amp hours per day. One rule when it comes to batteries or deep cycle batteries is that we do not want the battery to go below 50% of its maximum charge, because if it goes below that, it won't be able to hold its charge as much as it would be if it did go below. So we multiplied that by 2. So the minimum battery size we would want is 60 amp hours. So we found an available size above 60 amp hours, which was the 100 amp hour battery. We selected a gel battery because it is designed for long durability, such as temperature ranges and such, and the maintenance is a lot easier compared to other batteries, so we would not have to check up on it as much as other battery types. And now I'll pass back to Dean, who will talk about some future results in our future plans.
Here's currently our installed system. Here's the shed right here. The solar panels are installed pole mounted on top of the shed. The pressure tanks are here behind the shed, and our electric components are housed inside the shed, which is not shown here. And how we evaluated our system, to make sure our system met the customer requirements, was the charge time, which is the time it takes to fill up the tanks with using our pump, the total gallons that was able to store, the flow rate of the pump, and the flow rate of the drip irrigation system. And our target ranges are set here. Two main ones I want to highlight are the charge time and the total gallons stored. As you can see, our actual charge time was a lot less than our target range, at about 40 minutes, but our total gallons stored was at about half of what the customer required. And the reason for this is when we got the pressure tanks from the vendors, we asked them if the maximum acceptance factor was any problem, and they said that it wasn't, but as it turns out, it's about 45%, so the 86 gallons that each tank is spec'd at, it can't actually be filled up with water for the complete 86 gallons. It's only 45% of that. That's why our maximum that we found that we were able to store is 149 gallons. So as you can see there, we did not meet our customer need there. However, after talking with our contact at Walden West, we found that they divide their garden into 4 sections, and they irrigate one section at a time. So they ultimately only need 75 gallons at any point in time, but 300 total. So with 150, they're able to irrigate up to 2 sections at a time, and if they desire to do any more than that, they can just leave the pump running on and it can go directly. So we're able to still meet their needs. And based on our results, we're able to measure that, as Ken mentioned earlier, there's initial baseline pressure stored inside the pressure tank, and it's set at 40 psi. And to get our maximum water storage in there, we lowered it to 25 psi. And as seen here, we're able to generate more water, or we're able to pump more water through the tanks as we lower the pressure inside the tank, because obviously the pump doesn't have to work as hard to pump against the high pressure stored inside. And our flow rates are right here, which are the average flow rates, which are still above 4, which is desirable because with our pressure regulator, we're able to slow it down to meet slow it down using pressure to meet the 2 to 4 GPMs required to irrigate the garden. And our educational components are still being developed right now. Since it is a hands-on science camp, we're working on developing a lesson plan that's both hands-on as well as a display board, so that the field instructor can instruct the students, demonstrating how our system meets the lesson that they're learning for that day. And shown on the screen is our budget. Total it took to complete our project was around $4,800. And as seen right here, the 4th line item is the pressure tanks, and that's the most expensive part. But it does add educational value and was requested, and we just wanted to point that out. So the next steps in our process to complete this project, we have to install our final breaker, because to run our tests, we have a smaller breaker and a smaller 15 amp hour battery there right now. So because our 100 amp hour battery isn't installed and the breaker is being ordered right now, so when that's there, we can install that. And the conduit, we need to install conduit because the wiring right now is really rough and it's not safe for students to be in and out of that, to go in and out of that shed at the moment. And once that's installed, our contact at Walden West is still working on the piping to connect our system to their current drip irrigation system. Once that's set up, we can run our test to make sure that our flow rate is at what it's set at based on the pressure regulator, and as well as we need to complete our lesson plan and display board. And we'd like to acknowledge Dr. Shobha Krishnan and Tim Height for advising us on our project, our contact at Walden West, Richard Reed, Mike Ostrowski, who helped us install the electrical components and made sure we didn't get electrocuted or anything, Doug and Mary for giving us feedback on our first draft of the lesson plan so far, because they do teach science in the grades at the Walden West targets, as well as Santa Clara University School of Engineering, as well as S.D. Bechtel Jr. Foundation for helping us with our funding so we're able to complete our project. And thanks for coming out to our presentation, and we'll now open up for any questions you may have.